Okay, we're going to be talking about homework 1, part B, part 1. Three identical tanks with a cross-sectional area of 1.2 meters squared, and they have a bottom drain hole of 0.2 meters squared, and they're in a series. The flow tank was first maintained at 0.5 meters per third second until it reached steady state, and then the flow was increased by 10%, and we're going to simulate the levels, the liquid levels in the three tanks as a function of time. So we're going to start out by writing down our variables. So E equals 1.2, A out equals 0.2, and then we have G equals 9.81, Q in steady state is equal to 0.5, and then H at steady state. So the height at steady state are equal for all three. So this is going to be from Bernoulli's equation. We know that pressures cancel out and V1 is 0. So we're left with just a couple variables. We have Z, and we'll change that to just H. And we'll introduce A out on both sides of the equation so that we can introduce Q in, because A out times V2 is going to be Q out, and Q out equals Q in a steady state. And all we have to do is just move everything so that H is on the left side and everything else is on the right side, and that ends up being A out divided by Q in steady state divided by, or no, not divided by, squared, and then divided by 2 times G. Okay, so there's that, and then we can start defining our right-hand side. So right-hand side, so we want it as a function of time, and we want our vector V, and our vector V, we'll unpack it as H1, H2, and H3. And this will be equal to V. Okay, and next is the Q in is equal to Q in steady state times 1.1, and then we have our Q1 and Q2 and Q3, which all have new values. So, and this will be calculated again with Bernoulli's equation. So we'll have, and it'll be in an array. So we'll have Q, or not Q, A out times the MP dot square root, and 2 times G times H1. Okay, there's that. And we'll have, A out times MP dot square root. Then, yep, that's everything that we need right there. And then we don't want that return though, but we do want an array, B dot array, and we're going to return the DHCT values for each H. So that'll be Q in minus Q1 divided by A, and then Q1 divided by Q2 divided by A, and then we want Q2 minus Q3, and then divided by A. Okay, so we'll return that, get out of the indent, and then we will set our Tn for our IVP, our IVP, and then that will set that equal to around 100. Okay, and then we can do our IVP. So we have sol, or I guess we'll just do result, and then solve. So yeah, it's kind of what we want, but we also need to do our dense, dense output equals true, and then we can do our method. That needs to be a capital T. True. And then we can do our method equals rad val. Okay. Oh, forgot the. Okay, we need res and then shift enter. Oh, we need a colon right there. Okay, and then shift enter. Alright, so it did it through 0 through 100. And we have our H1s, H2, and H3s right here. And for each time value that we had. So, and it's true, so we can start coding our plots. So we're just going to do t plot equal to np dot lin space from 0 10, yeah, I mean 1,000 words, that's fine. We don't want that though, so we want h1, h2, h3 equals res dot sol plot, and then we want fig equals make subplot, and then fig dot add underscore scatter x equals t plot, y equals h1, and name equals h1. Alright, so it's going to fill out the rest of that for us. Okay, enter. Oh, needs to. Okay. Alright, and then we can hit shift enter. So there's a graph. We can clean that up a little bit. Fig update underscore layout. Let's have width equals 800 and height equals 500. And then our template will equal plotly underscore dark. Shift enter. Alright, so here's our plot right here. Converges at 0.38. Around, looks like 15 seconds. So we can change that a little bit still. So it's not so spread out. Where's our team? So 50. Shift enter, shift enter. Alright, I mean, that's fine. So, yep, so it converges right here. So just go back over what we did. We have our right-hand side right here, which gives us our dh over dt that we end up with. This dh dt is then solved in the initial value problems. It solves our dh dt and then uses that time to go into the future with it and see what the h's will be, and then these h's are then fed back in. The q's are then adjusted, and then it keeps repeating until it ends, and then that gives us our values, and we then graph them. So, and then now we'll move on to part 2 of this assignment. Okay, so we're going to move on to homework, or part 2 of this assignment. So this is basically, we're setting a set point for the third tank at 10% higher than the original steady state, and we have a controller game that we'll be experimenting with and see how it affects the tank levels. So let's go here and we'll set our H3 set point, and that's going to equal H underscore steady state times, we want to raise it by 10%, so 1.1, and then we'll set our KC equal to our first value of 0.1, and then we'll come down here and we'll add plus our KC. It has it for us already. Alright. Okay, so we want our H3 in our set point to be the first number that in our H3 is going to subtract that from that, because if it's our set point is higher than our H3, then we want it negative because we want more flow to come in, or we want less flow to come in, and the vice versa is true. If our H3 is more, or sorry, I had that backwards. If our set point is higher than our H3, then H3 is going to be lower, and we want a positive value. So we want the flow to be up, and then it's the opposite. If H3 is higher, it's going to give us a negative value, and it's going to decrease the flow a little bit more. So we'll go ahead and see. We'll go ahead and shift enter. So 0.1, you can see it's going a little bit higher than the 0.28 right here that we had, and yeah, so it corrected a little bit, went higher, then went back down, nothing too crazy. So next number we'll try is 1. And you see the overcorrection starts to begin. We go up and then we go down. Basically, the beginning KC, or this 1 KC value, is starting to add a little too much water at the beginning, and the next time it takes a reading, it's too high, and it starts taking a big chunk out and starts to level out again. But it's not too crazy. We'll try, what's the next number? 3, 5, 6, 7. Okay. So we'll try 3. So 3 obviously gets a lot worse. Overcorrecting, then a big undercorrection, then overcorrection, and then slowly kind of gradually gets down. And 5, shift even worse. But you can see the trend going on here: overcorrection, undercorrection, overcorrection, until it kind of settles out, and then 6, shift enter. Again, same issue. It's going up, down, up, down, up, down. Alright, and then we try 7 here, and then we have shift enter, and more influx, and it keeps on going. So you see the pattern here: overcorrection, undercorrection, overcorrection, undercorrection. I think that was the last one. Yeah, so the impact that the controller gain has on there is that the higher it is, the more sensitive it's going to be. I mean, even if you have the smallest error, it's going to have a huge impact on how much water is coming in, or how much of anything is coming in. So yeah, so if you have a big 7, you have a big number like 7, it's going to be a huge overreaction if there's too less of water in there. So yeah, so that's how the KC affects the water tank.